Hello everyone. Today we're starting a super interesting chapter, Unit 4, Moving Charges in Magnetism. Now don't worry about the name, we're going to make it really simple. This introduction is actually very important, not just for your board exams, but for understanding all of modern physics. So chalo, let's begin.
So, to get started, let me ask you a very simple question. You've seen a battery, right? And you've definitely seen a compass. But have you ever stopped to think, is there any connection between the two? I mean, what could a battery that powers things possibly have to do with a compass that just points north? Let's find out. You see, for most of human history, for more than 2,000 years in fact, everyone thought electricity and magnetism were completely separate things. It was like they lived in two different worlds. On one side, you had electricity, things like lightning or the static shock you sometimes get, and on the other side, you had magnetism, compasses, magnets sticking to each other. Nobody for a very long time thought they were related at all. And then, this man entered the story. Let's meet our hero, the Danish physicist Hans Christian Ørsted. The year is 1820, and he is about to make a discovery that will change science forever. And the best part is, it was completely by accident. So, picture this. The scene is a university classroom, pretty much like the one we're in now. Ørsted was giving a lecture, doing a demonstration for his students. He had a simple setup, a wire connected to a battery to show electric current. And just by chance, on the same table, there was a magnetic compass lying around. And then he noticed something that just wasn't supposed to happen.
Let's break down exactly what he saw step by step. First, a wire is connected to a battery, so an electric current starts to flow. Okay, simple enough. Second, a magnetic compass is just sitting nearby. And then, the magic moment. Step 3, the instant that current starts flowing through the wire, the compass needle suddenly deflects. It moves. This was the big shock. An electric current was affecting a magnet? How was this possible?
Now, Ørsted, being a true scientist, didn't just say wow and move on. He started investigating. He asked, okay, what's happening here? And this is what he found. If he reversed the direction of the current, the needle deflected in the opposite direction. Interesting. He also saw that if the current was stronger, the deflection was bigger. And if the compass was closer to the wire, again, the deflection was bigger. But the most important clue was that the needle always tried to line up in a circle around the wire.
To actually see this invisible force, he did something very clever. He sprinkled tiny iron filings on a piece of cardboard and passed the current-carrying wire through it. And would you look at that? The iron filings arranged themselves into perfect concentric circles, with the wire right at the center. This was like drawing a picture of the invisible force. It was undeniable proof.
So what's the big idea here? The main point. After all his experiments, the conclusion became crystal clear. An electric current, which is nothing but charges in motion, creates its own magnetic field in the space all around it. That is the connection. The big secret was out. Electricity and magnetism were not separate worlds after all.
And beta, here is the exact sentence from your NCERT textbook. For your exam, this is the golden line. Ørsted concluded that moving charges or currents produced a magnetic field in the surrounding space. Please write this down, remember it, because this is the precise wording that will get you full marks.
Okay, now everybody pay attention. This is a very important point. I call this a silent killer. It's a small misunderstanding that can quietly cost you marks in your exam. So let's make sure we clear up this confusion right now for good.
Now, look very closely at this slide. On the left side, you have a stationary charge. It's not moving. Its velocity is 0. As we learned in Chapter 1, what does it produce? Only an electric field. Simple. But now, look at the right side. The moment that same charge starts moving, it gets a kind of superpower. It now produces both an electric field and a magnetic field. So the key is movement. A moving charge is the source of magnetism. This difference is the most important concept from this whole introduction.
You know, that one small, accidental discovery in 1820, it started a revolution. It led directly to James Clerk Maxwell, who unified the two forces into one complete theory of electromagnetism. That theory then predicted the existence of radio waves. And that discovery, well, it's the foundation for almost every piece of technology you use today. Your phone, your Wi-Fi, radio, TV, it all started with that little twitching compass needle in a classroom.
So, to quickly revise, what are the key points from today's discussion? First, electricity and magnetism are deeply connected. They are two sides of the same coin. Second, a moving charge, or an electric current, is what creates a magnetic field. Third, if a charge is stationary, it only creates an electric field.
And finally, remember the shape. The magnetic field lines around a long straight wire are perfect concentric circles.
And that leaves us with a fascinating question to think about for our next class. We've established that a moving charge creates its own magnetic field. But what happens if this moving charge enters a region where a magnetic field already exists, maybe from a big magnet? What kind of force will it experience? That is exactly what we will explore next. See you.